take it away, Doug Ellison.
Right, so, for those of you who don't know and weren't paying attention yesterday, my name is Doug Ellison. I'm a visualization producer at JPL. I work in a group of about 8 people, programmers, 3D artists, back-end technical guys and things like that. And I thought before I show you kind of the money shot today, I'd tell you briefly what it is we do. Our group does a mix of things. Trent, could you do me a huge favor and shut that door?
Yeah.
Thank you. We do a mix of things. We do 2 kinds of graphics. We do rendered 3D animations, and we do real-time 3D graphics. Essentially, computer games and Pixar. Think of it that way. And our group has actually been responsible for a whole bunch of stuff you've probably seen in the past few days. This animation of Gale Crater that's talking about how, where the science is with Gale Crater, what it looks like. This is something I made in conjunction with MSL's project scientist about a week ago. He needed an animation to go with his press conference, so we said, right, well, let's find the best data we can. Let's try and break down the story you're trying to tell and turn it into something 3D that tells our story as best we can. If you've seen the MSL animation, and I'm sure you have, let's get to an interesting shiny bit. Here we go. This was our group as well. I was the technical director on this thing, and I had to work with people like the amazing Alan Chen, who you met yesterday. We had to basically go to him and say, right, how does your spacecraft work? What does it do? What's it going to look like? And he gave us assets, resources, simulations from which we could build these graphics. Now, they look shiny and exciting and so on and so forth. But it's actually based on real engineering simulation data. It's trying to be as accurate as it possibly could. Our job, both with rendered graphics like these and real-time 3D graphics that I'll show you next, is to take what the scientists and the engineers get up to and try and explain it to you as best we can with all the tools available to us. And rendered animations like this is just one of them. Now, I've just shown these, so if you have questions about how we do this sort of stuff, what the rules are, where we get it done, things like that, by all means come and track me down and speak to me about this. If you want to complain about the fact that the sound in this animation in space, come and talk to me about it. I can explain why there is. But what we're really here to do is talk about some of the real-time 3D stuff you can take home and play with yourselves. And so you know that I'm not cheating. I've just opened a web browser. I'm on the same Wi-Fi that you are, and I'm going to hit a button which takes us straight to the real Eyes on the Solar System website, solarsystem.nasa.gov/eyes. You'll get a web page that looks a bit like this. If it doesn't look a bit like this, then what you don't have is the Unity 3D plugin. It'll ask you to install it right here. It's about a 2 megabyte download, and it acts as the 3D engine that drives Eyes on the Solar System, as well as another tool I'll show you, Eyes on the Earth. It runs on Mac or PC, on Firefox, Chrome, Safari, Internet Explorer. Now, we do get bugs. This is still in beta. And most of those bugs, unfortunately, come from the nature of being a plugin inside a browser, and most of them seem to come with Firefox. Try Safari, try Chrome, even try Internet Explorer. It seems to work okay in there as well. I'm using Safari right now. Hey, 60% of you are using it, so. Show of hands, who uses Safari? Chrome? Yeah. Firefox? IE? Wow!
Nobody's going to admit it.
So, once you've installed the Unity 3D plugin, you hit Explore the Solar System. If you want a little bit more information on how to use it, you can hit these tutorials. Some guy with a strange British accent will walk you through some of the basics of Eyes on the Solar System and how to use it. If you hit this intro button here, you'll get a YouTube video that explains some of the basics about Eyes on the Solar System, what it's for, what it does, what it's all about. But in the meantime, I'm going to show it to you myself. The first thing to do, once it's loaded, is to get rid of the browser. Let's go full screen. All you have to do is hit this little full screen button right here, and now we're in full screen. What we have is, as a real-time 3D experience, we give you the planets, their moons, asteroids, comets, and a whole bunch of the spacecraft that have been exploring them, all the way from 1950 to 2050. And if you've ever used Google Earth or Google Maps or something like that, it's not going to be entirely unfamiliar to you, because you just grab your mouse, click and drag, and it's just like using Google Earth. And you say, well, actually, I want to look at, let's find something interesting. I want to look at Pioneer 10. You double click on Pioneer 10, we fly through something like 10 billion miles of interplanetary space. And here we are on board Pioneer 10, looking back at the solar system, as it is right now. Now, we give you 100 years of exploration here. And so we have to give you lots of different controls to get around, not just in terms of space, but also in terms of time. So if you get lost, stuck behind one of Jupiter's moons, upside down, backwards, and don't know where you are anymore, hit this home button here. We take you straight back to the top of the solar system. If you get really confused and start playing with some of the controls, the cameras, the lights and things like that, just double click the big logo and we reset everything for you back to this default view with all of the default settings. Now we can actually go and recreate, using this data, lots of different things that have happened in the past or are going to happen in the future. But there is a caveat to be said here. We have two kinds of data in the spacecraft. We have predicted data and we have reconstructed data. Now the reconstructed data follows with a couple of months lag. For example, we had a trajectory for MSL that goes all the way from the Earth out to Mars that started at 10:20 yesterday morning. Because the launch was scrubbed, we don't have a trajectory for the launch today, so we had to turn MSL off. In a few days' time, the engineering team will have a new trajectory for us, and we'll put that in and we'll be able to ride along with how MSL gets all the way to Mars. With Cassini, going back in time, you have reconstructed data that shows what the spacecraft actually got up to, and I can show you that as well. But we also have the rest of the mission going all the way out to 2016 and beyond, and that's just a predicted trajectory of where it's going to go. So there are caveats to be had. It's a mix of predicted data and reconstructed data. Let's go and ride on board something and have a little look around. Let's go and ride on board Voyager 2. The first group got Voyager 1. You guys are going to get Voyager 2. This is where Voyager 2 is right now. It is November 26, 2011 at 7:43 in the morning. God, that's early. And of course, Voyager 2 flew past Jupiter, Saturn, Uranus, Neptune. And all of those flybys are in here. We have the complete history of the Voyager 2 mission. If I wind back time here, we get closer and closer and closer towards the solar system. I'm running time backwards at many, many weeks or months per second. And you can see we're just getting closer and closer and closer. And eventually, we get to some of these flybys, and eventually we can actually find ourselves to one of those flybys, get a nice camera view, and enjoy that flyby. But it can be tricky to find these events. So what we've done is put in some bookmarks. We've bookmarked key events underneath this Destinations tab here. If you roll out the Destinations tab, on the spacecraft, you'll see different categories, because we've got about 30 or 40 different spacecraft in here. Under Outer Planet missions, you'll see we have different spacecraft listed. Juno, Pioneer 10, 11, Voyager 1, 2, Galileo, Cassini, New Horizons, Juno, and the potential mission could happen in the future called JEO. Under Voyager 2, let's go look at, we did Saturn flyby for the first group. Sorry guys, you're going to get a Jupiter flyby. And you may have already been looking for something. You may already be on a specific spacecraft at a specific time, looking at a specific view. And so we're going to go to a different time and place, so we ask you first. We're going to change your date and time, is that okay? And we go back to July the 9th, 1979. I was 6 months old. And here's Jupiter. And here's the Voyager 2 spacecraft active during that time. Now we're doing 57,000 miles an hour at this point. But because of the distances involved, it doesn't really look like anything's actually happening. So we have to kind of use a time-lapse mode to really enjoy what went on. So this control here, let's use time-lapse mode. This is just for fast-forwarding and rewinding. This is for a time-lapse mode. Let's run it at a couple of minutes per second. Here we are at 10 minutes per second, doing that flyby. And for a different view, a view that you may find pretty useful, click on the object that you're trying to follow along with, Voyager 2, and hit this camera control here. It's kind of an over-the-shoulder view. And then right-click on the thing you're interested in, and hit lock on. Now we're riding on board the spacecraft, but looking at the thing of interest. And we're still running at 10 minutes per second forwards, but then I can rewind time and let's back it up a little bit. Let's go a little bit quicker forwards. So now we're running at almost an hour per second. Duck, here comes Ganymede. Back in the 1970s and 1980s, we'd have had to rent massive supercomputers to produce 3D graphics that didn't even look vaguely good as this. But because we have modern gaming technology that we can stuff inside your web browser, you can be the director, the producer, the cameraman of all that, all on your own, in real time, with all of these missions. Now, this is one of those cases where we have to speed things up to see that something's actually happening at all. If we go back to the real rate, nothing's really happening. And this is true of more recent missions, like Cassini. Let's go on board Cassini when it arrived at Saturn. We're now jumping forwards to June the 30th, 2004. We load the spacecraft, here it is. There's the Cassini spacecraft with Huygens still attached, the Huygens probe that landed on Titan. And you'll see the main engine is already burning. Let's wind time backwards, let's rewind time. So here's Cassini just before it gets there. Now it's running a time-lapse mode, a couple of minutes per second. You'll see the The spacecraft goes through the rings using its antenna, its white high-gain antenna, as a primitive shield. The engine fires. The spacecraft slows itself down into orbit around Saturn. The engine will stop firing, and then it will turn around again and face us to use that antenna as another shield as it comes back out the other side of Saturn's rings. Saturn's rings are very, very beautiful, and it looks like they stop in a straight line, like that, edge of the rings. They actually go on for many, many more tens of thousands of miles. It's a very diffuse, and for a spacecraft, potentially dangerous belt of very small particles. So that's why the spacecraft turns to face us as it goes through the ring plane, use our antenna as a primitive shield. Now, this is this reconstructed data, so not only do we have the trajectory of the spacecraft, we have what the spacecraft actually got up to. Every turn, roll, pitch, and yaw you see here is what the spacecraft actually did. Wow. And there's about 6 years of it for you to play with. You can run this at an hour per second for a whole working day and not run out of this.
Oh, I will.
I have. At a conference, I had a projector and a plasma. I was doing demos like this for people walking past. I had another laptop just running Cassini all day. Now, we were using this at 6 minutes per second because whilst this was an incredibly fast, incredibly exciting event, things kind of happened quite slowly. But that's not always true. I'm going to back to our real rate of 1 second per second and do a different flyby. An Enceladus flyby. And the moment it loads, I'm going to hit pause because this gets a little bit exciting. Notice we now have a new Cassini without Huygens. We dropped that off when Cassini first arrived at Saturn. And here we are above Enceladus. Who has heard of Enceladus? Not enough of you. Right, Enceladus. We thought Enceladus was a dead lump of ice, about a 300-mile wide moon of Saturn that sat there just as a big, fat, tedious, boring ice cube. Turns out when we got there, the south pole of Enceladus is anomalously warm. It's really quite warm, like many tens of Kelvin above the rest of the moon. Then we looked even closer still. We saw that it was spewing vast quantities of ice out into space. We call it cold faithful, right? It's spewing vast quantities of ice into space, producing its own ring around Saturn as a result, the E ring. And so we've changed some of Cassini's trajectories. We've actually said, let's fly a little bit closer to Saturn. In fact, let's fly straight through the edge of those plumes spewing out of the South Pole to find out what they're made of, what they're like, what's causing them, where they're coming from. And some of these flybys have been incredibly close. We're about to do a flyby at an altitude of about 25 kilometers, about 15 miles. I'm going to unpause it, and remember, we're not in an accelerated mode. This is real time. If you could have been on board Cassini, this is the view you'd actually have had. This is how close we actually got to Enceladus back in October of 2008. What's funny is the engineers made the same sound when I showed them this. Now they knew the accuracy of that spacecraft. They knew it to less than a kilometer. The navigation on this sort of thing is astonishing. In a distance of about 1 billion miles, their accuracy is significantly more accurate than a mile. It's astonishing. So they can do this with confidence repeatedly. What we can do now is look at this reconstruction and say, well, how close did they actually get? Let's pause, and let's just zoom out a little bit. And we have a virtual tape measure. We can say, well, I want to right-click on Cassini, measure distance from, left-click on the Enceladus, and we put you a virtual tape measure through space. This little blue line is now your virtual tape measure that's running in real time. So as I run time backwards, you'll see we get closer and closer and closer. The numbers get smaller and smaller and smaller. That's about as close as we get, about 14.4 miles.
Wow.
I appreciate there are some foreign nationals in the room. 23.1 kilometers. I'm British, I speak miles as well, I'm sorry. And you can measure the distance between anything. You can say, hey, I want to measure the distance between, I don't know, Jupiter and Stardust in 2008. It was 523,544,455.8 miles at that moment in time. A one-way light time of 46 minutes, traveling at the universal constant of the speed of light. So you can measure anything. You can measure the distance from the Earth and Mars and see how it changes as we get through different launch opportunities and things like that. It's a really powerful tool, especially a useful educational tool as well. I'm going to show you one more thing that you may find useful here. Go back to the present day. And we've put in some features about some of the spacecraft that we have exploring the solar system. We've put a whole feature under here about Juno. There's another one all about Stardust. Another one all about the Epoxy flying past Hartley 2. And when we launched our Juno module, we also launched something else. Put on your 3D glasses.
Okay.
about the same. We've not done anything yet. But we have a 3D mode just for those glasses. Under visual controls, it's view in 3D. It's imaginative, right? And now it's a 3D anagram.
Wow.
Whoa.
I wish I could bottle that and take it back to our development. And a really good spacecraft to look at, one that's going to hit us in the head repeatedly. Now, when we transition from place to place, this can get a little bit kind of jarring. Let's go look at Pioneer 10. Now, this isn't perfect. It's a pretty crude way of doing it, but think about some of the math problems going on here.
Yeah.
Like, your eyeballs are this far apart to look at a little screen. But how far apart your eyeballs have to be to look at the entire solar system in 3D? It turns out your eyeballs, to get a view like this, end up being several hundred million miles apart. It's a non-trivial math problem to do this. And to give you a clue at what might be coming up in eyes on the solar system, I'm going to turn on some of the background stars here. And see if we can find a constellation we might be able to recognize. If anyone spots Orion, it's down here somewhere. There's Orion. Okay, there's Orion right here. Orion's belt right there. Let's get rid of the menus in the way. There we go. Let's zoom out and zoom out and zoom out and zoom out and keep zooming out. That's several thousand local stars in their actual place in 3D space.
And those are like actual positions of
Those are actual 3D locations of stars with their brightness and color derived from actual brightness and color measurements. There's something called the Hipparcos star catalog. And we can actually keep going. Wow.
Are you kidding?
Wow.
That's basically the entire observable universe. I intentionally bought a mouse that has a little clutch on it, so I can click and zoom in, or I can just let it freewheel.
I think we died right there.
You don't know. I was determined to walk towards the light. Right, 3D glasses off. I'm going to show you one more thing before we get out of here. Now, before Eyes on the Solar System, there was a project called Eyes on the Earth. And the abilities of Eyes on the Earth are about to be ingested into Eyes on the Solar System. So this tool here, which was before Eyes on the Solar System, lets you pull in real data that these spacecraft have actually taken. And that's going to be living inside Eyes on the Solar System in the next couple of weeks. What we've got here is a whole bunch of NASA's Earth-observing satellites. It's one of JPL's dirty secrets is that we actually, you think we build robots to explore the solar system. We actually build robots to explore the Earth as well. And here's a whole bunch of them. If we hit real time, we get to see where these spacecraft are right now. And we can say, you know what, I want to look at data from Aqua. And so here's the Aqua spacecraft. Let's put a little floodlight so we don't have a shadow behind the Earth. And right here, we can pick different data sets. Now, the data sets drop in and drop out, depending on how healthy the pipeline is. But we can say, I want to look at carbon monoxide from the last 3 days. Now, this isn't just a pretty picture. You can see it's got different colors in here. You've got blue areas that on this scale at the bottom you can see are kind of low, and red areas that are high. When we roll the mouse over the map, we get an actual quantitative value being read off the map for you. So where the mouse is here, 132 parts per billion of carbon monoxide, measured at an altitude of 18,000 feet. If we go down here, it's only 57 parts per billion. And we can actually bring in multiple days worth of data. We can say, well, actually, I want to look at, like, let's look at those 3 days of data right there. As luck would have it, I picked where there's no data at all. I have a fallback position. We have events. We've put in a couple of bookmarks, just like we do with Eyes on the Solar System. We've only got 2. We're going to have a lot more in the new version of this. Let's hit the station fire. This was a fire that happened in Southern California in August of 2009, I believe. And this is the result of forest burning behind LA back in August 2009. It doesn't appear directly above LA. Because we're measuring this at an altitude of 18,000 feet, it ends up downwind of LA before this instrument picks it up. This is real data that shows how massive that fire was on a global scale. It really was kind of a global event. But I'll show you one more thing before I let you go that kind of really puts it into context. So here is the results of that station fire over a couple of weeks.
Wow.
And for people in LA, this was a big deal. JPL itself was shut down for a whole day because the fires got within about a kilometre of basically our back gate. And you might think, well, that's actually a pretty massive event right there. I'm going to pause and I'm going to choose any Halloween time. Let's go back to October 2010. Let's just get 3 days here. And you'll be amazed just how much impact we can have on the world.
Wow.
That right there is the result of unsustainable /urban agriculture in the Amazon rainforest. That's a result of the exact same activity in sub-Saharan Africa. So you saw that little forest fire that's going for the station fire? This is what we can really do if we put our minds to it. And notice, because of circulation around the planet, what gets produced here kind of gets enjoyed by Australia. What gets produced here gets enjoyed by Africa. These gases don't end up just sitting around your back garden, they end up circulating around the globe. So that's eyes on the solar system, this is eyes on the Earth, which is going to be improved and look a lot more like eyes on the solar system very soon. There's one more thing I'm going to show you by way of a preview, and it is what almost everyone has asked when they come to a demo like this is, when can I have it on my iPhone/iPad/ generic mobile device here? We've taken the idea of eyes on the Earth and put it on cell phones, and it's going to be in the App Store for free in a couple of weeks' time. It's called Earth Now. It's right here. And you'll get a 3D globe that looks just like this, and just like eyes on the Earth, you can pick and drag your way around, you can zoom in and zoom out. We're not trying to be Google Earth, we just want to show you some of this science data. And you can say, well, I want to look at the carbon monoxide now. Carbon monoxide. And we load it straight off the web, so it's absolutely the most recent data available every single time. So there's that exact same data on your cell phone with a whole bunch of the other data sets as well. This is called Earth Now. It's going to be on these shiny things in the next couple of weeks. And we'll be doing it on other devices, hopefully in the next 12 months. It's now time for you to go back to the tent.